When water moves into air-dry soil, it is only slightly affected by gravitation. Water moves upward and horizontally as well as downward. The principles governing water movement are graphically shown in this time-lapse study. In these demonstrations, soil is held between glass plates so that you can see what happens as the soil is wetted. The glass plates are a foot high and 2 feet wide, with about 1/2 inch of space between for soil. Think of this model as representing a vertical cross-section of a soil profile. Time-lapse photographic processes used here permit speeding up the action. In nature, it would require many hours for the water movement which you will observe in the film in only a few minutes. Using a motion picture camera, single pictures are taken of the models at short time intervals as the water moves into the soil. The time intervals are from 1 second up to 22 seconds. The completed motion picture film is then projected so that speed-up times in these sequences range from 24 times normal to as much as 500 times normal speed. The speed factor will be observed on a card above the model. Because water movement usually is rapid when water is first applied and is very slow at later times, the speed-up factor often is changed during a sequence. This is indicated by changing the arrow on the time card, which points to the appropriate speed factor. The soil used is an air-dry silt loam, which has been passed through a fine screen. Sands, clays, and aggregates made from the soil are used to simulate non-uniformities in the soil profile. Water will be added in a furrow or on the soil surface with a device which keeps the water level at any desired depth. Before you see the sequence using time-lapse photography, here are 2 demonstrations that illustrate the principle of capillarity. This principle is involved when water moves into dry materials. Liquid is pulled upward from free water in the dish into this porous ceramic rod because of the attraction of solid mineral surfaces for water, called adhesion, and attraction of water molecules for each other, called cohesion. Adhesive and cohesive forces then are responsible for moving water upward against the downward force of gravity. In the second demonstration, water rises between 2 closely spaced glass plates because of the adhesive forces between glass and water and the cohesive forces between water molecules. Cohesive forces near the air-water interface create a membrane-like surface, and water is pulled upward beneath this surface. The pressure beneath this negatively curved surface is negative, the opposite of the internal pressure of a raindrop, which has a positive curvature and is positive. Water in pores with a negative air-water interface may be said to be under tension. Now to the models and time-lapse pictures. It may be observed here that water moves outward from an irrigation channel almost as rapidly as downward. This is evidence that the forces responsible for this type of water movement are mainly due not to gravitation, but to the attraction of solid surfaces for water. As the soil becomes wetter and wetter, however, gravitation plays a stronger role, and if the soil becomes completely saturated, then gravitational forces predominate. The horizontal layer you see is coarse sand. One of the important principles of unsaturated flow of water is illustrated here as the wetting front encounters the coarse sand. The pores in the soil are many times smaller than those between sand grains. Water is held in these small pores by large adhesive and cohesive forces. The pores in the soil are like the pores in a piece of blotting paper used to soak up ink. The huge pores in the sand cannot hold water against the forces in the smaller pores above. Hence, the water does not move readily into the sand. However, as the soil above the sand becomes very wet, The water eventually moves into the sand in the same way as ink would drip from blotting paper which was excessively wet. The sand layer thus acts something like a check valve, holding the water back until the soil becomes very wet, and then letting the excess water pass through. What happens to water in soil containing a sand layer is typical in principle to what happens to water in soil situations where sands and gravels occur as layers in fine soil material. Much agricultural land, as well as land in turf and other vegetation, is layered in this fashion. In Washington State's Columbia Basin, there exists 250,000 acres of soil composed of 1 to 2 feet of fine sandy loam overlying coarse sands and gravels. The ability of this soil to support plant growth is greatly affected by the presence of coarse sands and gravels. Because of these coarse materials, the overlying soil can retain more than double the amount of water usually held in a fine sandy loam. This soil is one of the best in the basin. These principles are usefully employed in the construction of soil profiles in turfed areas such as playing fields and particularly on golf courses. Recognition of this principle is evident in the specifications for putting green construction adopted by the Green Section of the United States Golf Association. Now in this sequence you see a layer of fine clay in an otherwise uniform soil. This clay layer is similar to a clay pan or any type of layer in which the pores are extremely fine compared to the pores in the overlying soil. These layers often restrict rooting depth of plants and are particularly known for the trouble they cause in preventing downward penetration of water. When excess water is added to the soil, water tables often are built up over such layers. If they occur at shallow depths, water tables often rise above the land surface during wet seasons, imposing serious limitations on the use of the land. Despite the fact that a clay pan hinders downward movement of water, it does absorb water readily as the soil above is wetted. Observe the wetting front as it moves into the clay pan. The pores in the clay are much finer than those in the overlying soil, so that they can pull water from the soil. Water tables are not built up over clay pans because of inability of water to enter them. Instead, water tables result from slow transmission of water through them. The resistance to water movement in the extremely fine pores of layers like these is sufficiently great that, even over periods of weeks and months, little water is transmitted through them into the soil below. Where a soil profile may be artificially created, as in golf course putting greens, uniformity of soil mixtures is an important consideration, as is recognized in USGA putting green specifications. The extent to which downward movement is restricted and water storage is altered depends on the fineness of the pores and the thickness of the restricting layer. This is in contrast to what was shown earlier in soil overlying coarse sand layers. There, downward movement of water was temporarily checked, but water tables could not be filled up as long as the opportunity existed for free drainage into the coarse material. This model has the sand layer on the left and the layer of coarse aggregates on the right. These aggregates are about the same size as the sand grains but are made up of soil particles like those of surrounding soil. The large pores between aggregates are about the size of the large pores between sand grains. Water movement in soil materials, which wet readily, depends upon porosity. Each individual aggregate contains numerous fine pores of a size similar to the pores in the surrounding soil. Note that the small aggregates in the aggregate layer will wet up as soon as the wetting front reaches them. However, pores between aggregates are too large to pull water from the soil pores in the finer soil. Hence, the large pores remain empty. All of the water passing through the layer must first move through the fine pores of the aggregates and then across the contact points between aggregates. The small number of contacts between aggregates, therefore, restricts the rate at which water can move through the aggregate layer. If free water is supplied directly to a layer of coarse sand, water rushes in rapidly, filling all of the pores. These are conditions of saturated flow. The moving force is due to positive pressure from the water in the channel. Under saturated conditions, large pores can transmit water readily, but the rate of transmission depends upon the hydrostatic pressure of the water supply. The positive pressure is dissipated rapidly over a very short distance in the fine pores, giving way to adsorptive forces in the drier soil. Thus, water moves out into the soil from a sand layer under unsaturated conditions. It is pulled into and through the soil because of the attraction for water of the mineral surfaces making up the fine pores of the soil. The sand in the layer at the left is the same kind of sand through which water is flowing at the right. Here, however, the layer is not in contact with free water or water under positive pressure. Hence, the surrounding soil is wetted under unsaturated conditions, where the water is present only under negative pressure. The sand layer cannot wet until the water pressure in the films of the adjoining soil becomes nearly positive, which means that the soil becomes very wet. As this happens, the layer takes water. Porous materials with very large pores aid in movement only under conditions where they contact free water, that is, water under zero or positive pressure. Where water exists only under negative pressure, such material stops or materially retards water flow. A question frequently is raised: what differences in flow might be expected if underlying sands were moist rather than air dry? Here you're looking at dry soil overlying dry sand on the left and moist sand on the right. Since water movement has, so far, been detected by observing color change, a different technique is needed to help you see water entering sand, which already is moist. A chemical substance has been added to a white sand which, when contacted by added water containing another chemical, will turn pink. The water content of the sand on the right is about the quantity which would be present in a sand just barely wet enough to support plant growth. The presence of some water in the sand should make a difference in the tension when added water enters the sand. It may be seen here that water enters the dry sand at nearly the same time as it enters the moist. There is a difference in the rate and pattern of water penetration into the sand in the two cases, but in both the water retained above the sand is about the same. A fingering pattern develops in the moist sand because it already is wet, and a few of the smaller channels can readily transmit a little water, thus reducing the buildup of water above and flow in adjoining larger channels. Under many conditions in nature, including situations where irrigation is practiced, sands and gravels lying below finer soil materials are naturally moist. It is important to illustrate differences among uniform soils with respect to their ability to transmit and retain water, apart from problems of stratification. Note that the depth of penetration at any given time is greatest for the sandy loam, which has the largest pores, and least for the clay loam, which has the finest pores. The finer the pores, the more the rate of water flow is restricted. But after the water source is removed, the forces causing continued water movement are greatest in the clay loam, which has the finest pores, and least in the sandy loam with the larger pores. Despite this, however, the net useful storage is greatest in the clay loam and least in the sandy loam. Although a sandy loam retains less useful water than does the clay loam, it is nevertheless a good soil in an irrigated area where lack of water holding capacity can be compensated by irrigation. The infiltration properties are generally good. Clay loams, on the other hand, often are difficult to irrigate because of low infiltration rates. In dry climates with no irrigation, a sandy loam would not hold enough water to carry most plants through the growing season. A clay loam, by contrast, would retain more water over a longer period of time. The principles illustrated here have important application to situations where control of soil materials and profiles is possible, as in a golf course putting green, such as that specified by the USGA. Sandy soils are favored because they resist compaction, and their use is permitted because frequent irrigation is practical. Also, the presence of coarse sand and gravel layers in deeper soil increases the water storage capacity of such a soil. In the demonstration so far, your attention has been mostly focused on the movement of the wetting front. Now, with the aid of a soluble dye, the pattern of water movement back of the wetting front appears. Any water-soluble material which is not strongly absorbed by the clay particle will have the net movement you see here. The dye traces are not streamlines. The reason for this is that geometry of the adsorptive force field responsible for water movement is changing. The dye traces include the effect of any change in direction of water flow due to the development of a non-uniform field. Such a non-uniform field is produced as the two wetting fronts join. In the beginning, the dye moves radially away from the water source. This continues as long as the movement of the wetting front remains radial and uniform. Soluble fertilizer material, such as nitrates, moving with the water, will trace out patterns like these. The dye traces show the importance of proper fertilizer placement with respect to the position of the wetting stream in an irrigation furrow. Now consider what will happen to the dye spots midway between the two furrows when the two wetting fronts come together. Note particularly the middle dye spot at the same level as the water in the furrows. When the wetting fronts join, there is a radical change in the pattern of water movement. Water continues to move upward into the dry hill above and downward into dry soil below. That dye spot in the middle shows little movement because water flow above this level is upward and below it is downward. After the soil in the hill is entirely wetted, only evaporation will cause further upward flow. Such upward flow is of much practical importance. For example, soluble fertilizers and salts in the upward moving stream will tend to accumulate in the surface out of reach of plant roots. Such phenomena have been observed in numerous placement studies. A further illustration of how water moves in soil may be seen in this cross-section through an 18-inch mound or hill, simulated in an irrigation furrow in agriculture, or numerous planting situations, as with soil preparation for turf. Loose soil thrown up into a mound like this can be difficult to wet because of the presence of excessively large pore spaces. Excessive elevation differences, complicated by increasing porosity from the bottom of a mound to the top, can lead to poor wetting at the upper level. In potato culture, loose soil in hills has been observed to remain dry during an entire growing season, with important reductions in yield quantity and quality. Compacting the mound with a roller at planting time, as you see it on the left, can help in two ways. First, the elevation is greatly reduced. Second, the reduced porosity will help to increase the rate of upward water movement. Applied to soil conditions on a much smaller scale, the advantages of rolling or firming a newly planted seed bed, or for that matter, properly settling of an entire surface of a new putting green, are evident. A practical application of principles of water flow is shown here. Water moves rapidly into soil with good tilth. Proper tillage practices on the soil in the center have produced numerous small aggregates which have been stabilized by decomposing organic material. The resulting large pores, which remain open all the way to the surface, take water readily. Thus, the infiltration rate remains high. The same amount of organic material, when turned under in a layer, does little to improve soil tilth, and, if anything, makes conditions worse. The straw layer, like a sand layer, checks downward flow of water. In this case, not only does less rainfall penetrate into the root zone, but more water remains on the surface, making it vulnerable to damage from foot and vehicle traffic and the impact of falling rain. On the right, an irregular channel filled with coarse sand simulates an open channel left by mechanical aeration, or perhaps a channel left by decayed roots or burrowing insects or worms. Such channels or cracks do not assist in water movement when they are not open to a source of free water. They aid water flow only when they connect with free water at the surface. The principle involved also applies to tile drains. Water can move into such drains only if positive water pressure exists in the surrounding soil. Hence, tile placed in wet soil for drainage must be located below the water table if they are to be effective. On athletic fields or on golf course putting greens, where a soil profile is artificially created with a gravel layer and tile lines for drainage, tiles must be located below the gravel layer. Water moves rapidly into the soil through a vertical aeration channel filled with sand or coarse organic materials. But this is true only if the channel extends all of the way to the surface. Use of such vertical aeration channels has particular application on golf course putting greens or tee surfaces. It is of great benefit on compacted or thatched areas where infiltration rates at the surface are extremely limited. A vertical channel is cut into the soil with an aerifier. A top-dressing sand of a desirable particle size is then worked into the open aeration holes until they are filled to the surface. This makes rapid infiltration possible, permitting water to quickly reach and move into the underlying dry soil, thus reducing surface runoff. Since the water in the surrounding soil is under negative pressure, none has entered the channel on the right. The important point to remember here is that the channel or aerifier hole must remain in contact with free water or water under positive pressure to do any good. And if the top of the channel is covered over or becomes plugged, for instance by the application of a fine silt top-dressing material, water flow into the channel is restricted even though the soil might be saturated.